All right, so if you do know the ABCD matrix or any other matrix of a network, then you can basically come up with some very convenient equations, which I will only very briefly describe here. If you look at the notes, you will see the proofs for all of them. But at the end of the day, if we do know the matrix of a network, then we can very easily calculate what happens if I connect a source and a load. And so in this figure, you can see all the definitions for voltage and currents, as well as waves, A's and B's. And so, for example, a lot of times we like to understand what is the reflection coefficient at the input. If, for example, this linear network here was a transistor, and I say, OK, I connect my load to this transistor amplifier, what will be my reflection coefficient? Because perhaps I want to make this reflection coefficient to be 0, then it will turn out to be equal to this number that you see right here. Be careful, this is not S11. It would have been S11 if ZL had been equal to Z02. That means that gamma L basically would have been 0. But in general, ZL is not equal to Z02, and so that means that gamma in general is not S11, it's something different. And so that's probably the only thing that you need to really get in your heads, is that the reflection coefficient is equal to the S matrix only if each port is terminated to its own characteristic impedance. If it's not, then you have to use these more general equations both for the input and the output. And again, gamma L that you will see here is nothing else but ZL minus Z0 over ZL plus Z0. And similarly, gamma G that you will see here is nothing else ZG minus Z0 over ZG plus Z0. The last two equations also tell you that you can actually find the input and the output impedance directly if you really want to, by just correlating the load and the ABCD matrix, and similarly for Z out. So these are very convenient equations you can use anytime you want, and you have all of them. Another part that people will always ask is, what is the transducer loss or gain? Here's what we mean by transducer loss, and then I'll discuss gain. Transducer loss is nothing else but counting how much power goes to the load compared to the available power from my source. So if, for example, this is a matching network, then we expect this transducer loss to be a positive quantity, and we want this thing to be as low as possible. In other words, we want ideally PA to be equal to PL. But if this thing is an amplifier, then clearly the power that goes to the load should be much higher than the power coming from the source. And so this, in that case, it makes sense not to talk about transducer loss, but rather talk about transducer gain, which is exactly the opposite. So as you will see here, GT, the transducer gain, is PL over PA, while transducer loss is PA over PL. So, and of course, it's basically one is negative to of the other. The other, however, tricky thing to understand here is exactly what is PA. In other words, what do we mean by power available from the source? Power available from the source means that this is the maximum amount of power that this source could ever give you. And so that happens when the source sees its conjugate matching here. The maximum available power from the source, in other words, is the power you can extract from the source under conjugate matching conditions. So if you solve this very simple idea of having a source conjugately matched, then you will find out that the power available from the source is nothing else but Vg squared over 4Rg in RMS terms. Now you might say, why are you comparing the power that goes to my load to the power that is available from the source, and you're not comparing that to the incident power of this network, right? Perhaps the incident power of this network is not the same as the power available from the source. Well, the answer to that is make it to be the same. It's really your responsibility as a designer to take as much power from the source as you can. And so if you have made a mistake and you don't have conjugate matching condition here, or if you purposely don't have conjugate matching conditions, there are cases we'll see later on where that's not desired, then fine, but you should basically be fair in your comparison and compare to what you would have gotten from the power available and what you're actually getting from the system. Now, if you know the S parameters of the network, you can do these calculations, and as I mentioned, they're available in my notes. And so, for example, you'll find out the transducer gain is given by this equation here, or if you will, the transducer gain can be calculated directly by knowing the ABCD matrix of the network and then knowing the load and the impedance. Some people will also define the actual gain of the system, meaning they will compare their power that goes to the load to the actual input power, not the available power. And I'm giving you the equation here as well. But in my opinion, in most people's opinion, this is a far better metric than the actual gain, because the actual gain depends on how good of a designer you are, while the other one is a far more realistic comparison. Finally, there is this thing that we call mismatch loss, which we have covered a little bit before. But the whole point about mismatch loss is that we can essentially attribute part of the loss that we are not getting to our load to mismatch, meaning part of the power that we're missing and does not go to our load is due to mismatch, and part of the power that we're missing and it doesn't go to the load is simply resistive, meaning ohmic losses. And they're of two different natures, right? So the resistive loss is the amount of loss that this network here will consume because of having resistors, because of having ohmic losses. On the other hand, mismatch loss is really the power that will be reflected back. So it's not lost in terms of it doesn't turn into heat, but it is lost in the sense that it doesn't go to the load. So if you do the calculations, and again, you will find out this in my notes, you will basically find out that this is essentially the equation that will give you the power that goes to the load. So the power that goes to the load, as you can intuitively expect, will be equal to the available power from the source, 1 minus gamma in square. 1 minus gamma in square is simply the reflected power. So it is the power minus the reflected power, minus the power dissipated as resistive loss. So if you want to separate the two, sometimes you can write this transducer loss that we discussed before in the form that you will see right here, where it can explicitly give you the amount of loss you suffer due to mismatch, and that means make gamma in 0 if you don't want that loss, and the amount of power loss you suffer due to the ohmic loss, in which case it simply means use a better technology to have a lower loss system. These are a little bit more different expressions, different ways you can express exactly the same thing, just playing with equations to express, for example, the transducer loss here in dBs as a function of the ohmic loss and as a function of the mismatch loss.